we have a function here, f of x is equal to 6x to the 2/3 minus 4x, of which we will analyze in detail to find where it is increasing and if there are any local extrema. So to get started, first we want to take the first derivative, and to do so we can use the power rule to get 4x to the negative 1/3 minus 4, because 2/3 minus 6 is 4, you subtract 1 here, and this x cancels out. And now we set the first derivative equal to 0, and we can rewrite this as 4 divided by x to the 1/3 minus 4. And here we want to create a common denominator, so we can multiply the 4 by x to the 1/3 over x to the 1/3 to get 0 is equal to 4 minus 4x to the 1/3 over x to the 1/3, and this can also be rewritten as shown here using cube roots. So now we want to look at the numerator and denominator separately, and so when we set the numerator equal to 0, we can add 4 to the other side and then divide by 4 on both sides to get the cube root of x is equal to 1, and to cancel this out we can cube both sides to get x is equal to 1. And for the denominator, we can see that y prime is undefined at x equals 0. And now the most important part here is creating the number line, and we can see we have 0 and 1, and to test if it is where it is increasing and decreasing, we can plug in values to the left of 0, in between 0 and 1, and any value that is greater than 1, which I did so here. I chose -1, 1/2, and 2. So when we plugged in -1 into the first derivative, we got -8, which is less than 0, so we know it is negative here and it is decreasing. And when we plugged in 1/2, we got a value that is greater than 0, which is increasing. And for 2, we got a value that is negative, so this part of the function is decreasing. So therefore we can see that f is increasing on the interval 0 to 1, which is here, and f is decreasing on the intervals -infinity to 0 and 1 to +infinity. And therefore f also has a local minimum at x is equal to 0, which is right here, and a local max at x is equal to 1. So to finish analyzing our function, we want to take the second derivative, and to do so we can use the power rule again to get -4/3 x to the power of -4/3, because -1/3 times 4 is -4/3. You subtract the 1, cancel out the 4. Then we can set that equal to 0, and this can be rewritten as -4 over 3x to the power of 4/3, which can also be rewritten again as shown here to change this into a root. So therefore we know that y prime is only undefined at x equals 0. And to look at concavity, I tested -1 and 1, and when I plugged that into the second derivative, I got both values were -4/3, which is negative. So since it is negative on both sides of 0, that means it is concave down everywhere, or it is concave down from -infinity to +infinity. So there's no concave up anywhere. And there's also no inflection points because the concavity does not change. Since it is both concave down here and here, 0 is in fact not an inflection point. So we can check what we found analytically, graphically. So here's the function, and we can see that it is decreasing from -infinity to 0, and it is increasing from 0 to 1, and it is decreasing after that. So here's our local min, and here's our local max. And we can also check that the concavity is concave down everywhere. And to look at the derivative of the function, we can check to see that y prime is undefined only at x equals 0.
All right, so for part 2, we employ the mean value theorem on f of x equals 6x to the 2/3 minus 4x. And we know that it's continuous on the interval 0, 2. So first we have to find the average rate of change using this equation, f of b minus f of a over b minus a. And we find that it is equal to 1.52 minus 0 over 2 minus 0. And 1.52 over 2 is equal to 0.762. So we know that this is our A rock. And then we find the derivative of 6x to the 2/3 minus 4x, and then we set that equal to A rock. So we know that 4x to the negative 1/3 minus 4 equals 0.762. Knowing this, then we add 4 to both sides. So 4x to the negative 1/3 is equal to 4.762. We also know from our exponent rules that 4x to the negative 1/3 is equal to 4 over x to the 1/3. So we cross multiply here, and we get 4 equals 4.762 x to the 1/3. Now we want to isolate our x. So we divide both sides by 4.762, and we get 0.84 equals x to the 1/3, which we then do our 1/3 root function on Desmos, and we find that x is equal to 0.593 by finding this and isolating our x. So now we know that at when x equals 0.593, the slope is going to be 0.762, which is our A rock value.
So for our third problem, it was an optimization problem, and we were told that a cylindrical can holds 300 cubic inches of frozen orange juice. So if you look at the image here, we know that the cardboard side costs 1 times per square inch to construct it, whereas the top and bottom are 2 times per square inch pricing wise. So when we write out our 2 different problems that we'll use, we have the surface area. This first part, 2 pi r times h, is for the side, plus 2 pi r squared references the top and bottom. We also have our volume equation, which is pi r squared times h, which we are told is equal 300 cubic inches. So then we isolate h, and we get 300 over pi r squared. Once we do this, we are able to optimize the problem by plugging this volume, or what we solve for h, into our surface area equation above. So here we have 2 pi r times 300 over pi r squared plus 2 pi r squared. When we eliminate the pi's from the numerator and denominator here, we end up with 600 over r plus 2 pi r squared. Once we do this, we want to find our cost function because we're trying to find the dimensions of the least expensive can. So for our cost function, we plug in our equation with referencing the fact that the side costs $1 per square inch, whereas the top and bottom are $2 per square inch. So once we do this, to simplify it before we find the derivative, I found the equation 600r to the negative 1 plus 4 pi r squared. After this, we are able to find the derivative of the cost function. So then we get negative 600r to the negative 2 plus 8 pi r. So by doing so, we brought the negative 1 down, so that became negative 600. We subtracted 1 from our exponent to get negative 2, and then we brought the 2 down from the exponent up here to get 8, and then subtracted 1 from the 2, which gave us the remainder of just r to the first power. Then we set our derivative to 0. After this, we want to solve for r. So first, I added 600r to the negative 2 to both sides. which gave us 8 pi r equals 600 r to the negative 2, or 600 over r squared. Both are the same thing. After this, we want to multiply both sides by r squared, so that left us with 8 pi r cubed equals 600. Once we do this, we're still isolating r, so we want to divide both sides by 8 pi. So we get r cubed equals 600 over 8 pi. Then we want to use the cube root to isolate r, and then we end up with r equals 2.879 inches. So that's our radius. After this, we want to solve for our height. So then we'll plug this back into our volume equation up here. So then we'll end up with 300 over pi times our radius, 2.879 squared, equals 3.666 inches, which is our height. Now that we have all of our variables, we can solve for our surface area. So we'll plug all of our new factors in. So we have 2 pi times our radius, 2.879, times our height, 3.666, plus 2 pi radius, which is 2.879 squared, which gives us the surface area of 118.394 inches squared. And then to check if it is a minimum or maximum, we can use the first derivative test. So by doing this, I plugged an r value greater than 2.879, so I plugged 4 into our cost function's derivative. When I plugged this in here, I found that it was a positive number, which therefore means it is going up here. And then when I plugged in a number less than 2.879, for example 2, I saw that it was a negative number, which therefore means it's going down, and that it is a minimum value, which means the concavity is up.